Traditional RAG systems follow a fixed sequence. They embed the query, search the vector database, retrieve the documents, and generate a response. The system has no way to check whether those documents actually answer the question. It cannot retry when retrieval fails. It cannot catch hallucinations before they reach the user. Agentic RAG changes this by introducing decision points throughout the workflow. The Agentic RAG system can now route queries to appropriate sources, grade documents for relevance before using them, and validate generated responses against source material. So let's talk about the fundamental limitations of traditional RAG systems because understanding these failure modes is important before we can appreciate why Agentic RAG matters. Traditional RAG follows a linear execution path. The query comes in and we embed into a vector. Then we search the vector database for similar content. Then we retrieve the top key documents. We concatenate them into a context window. And then we send everything to the language model for generation. This works reliably well for straightforward factual questions against well-indexed content. But the architecture has fundamental limitations that has become increasingly problematic as systems scale. So the first limitation is the absence of quality validation. There is no mechanism to evaluate whether the retrieved documents actually answer the question before sending them to the language model. The system retrieves based on semantic similarity, but similarity doesn't really guarantee relevance. A document might be semantically similar to the query but not actually contain the information needed to answer it. The second limitation involves complex query handling. Questions that require information from multiple sources or questions that need multi step reasoning cannot be decomposed into simpler subqueries. Traditional RAG treats every query the same way, regardless of complexity. The third limitation is the lack of fallback strategies. When the initial retrieval returns irrelevant content, the system has no recovery mechanism. It proceeds to generate a response from inadequate context, often producing answers that sound confident but are actually based on tangible, irrelevant information. The fourth limitation concerns hallucination detection. The language model may generate answers that sound completely plausible but contradict or extend beyond what the retrieved documents actually state. Traditional RAG has no built in mechanism to verify the generated claims are actually grounded in the source material. The fifth limitation relates to query ambiguity. Ambiguous or unspecified queries pass directly through the system rather than being clarified or reformulated. If the user's questions could be interpreted multiple ways, traditional RAG simply picks an interpretation based on whatever the embedding happens to retrieve. These limitations become increasingly severe as query complexity increases, as document collections grows to millions, and as accuracy requirements become more and more strict for production applications. In my experience, teams often discover these issues only after deploying to production when real users start asking questions that don't fit in the simple patterns that were used in during development. Now let's explore how agentic RAG approaches address these limitations by introducing decision-making capabilities into the retrieval workflow. Let's talk about what actually makes RAG agentic because the term gets used loosely and I want to be precise about the architecture changes that matter. Agentic RAG embeds autonomous decision making capabilities into retrieval and generation workflow. Instead of following a fixed sequence of operations, the system can now make choices at multiple points in the process. The first capability is query analysis. The system can analyze the incoming query to determine the most appropriate retrieval strategy. A factual question about a specific topic might route to a knowledge base. A question requiring current information might route to web search. A numerical analysis question then might route to a structured database. The second capability is the document quality evaluation. After retrieval, the system can now evaluate the quality of retrieved documents before using them for generation. Documents that do not fit actually address the query can be filtered out before they contaminate the context. The third capability is query reformulation. When initial retrieval produces insufficient results, the system can rewrite the query with different terms, expanded scope, or alternative phrasing to improve the subsequent retrieval attempts. The fourth capability is response validation. After generation, the system can validate the generated response against the source documents to catch hallucinations. Claims that are not supported by the retrieved context can be identified and addressed. The fifth capability is iterative refinement. The system can iterate through multiple retrieval and generation cycles until quality thresholds are met, rather than accepting whatever comes out of a single pass. The key architectural shift here is the introducing feedback loops and conditional branching where traditional RAG has only a linear flow. An agent can decide whether to retrieve from a vector database, search the web, query a structured database, or answer directly from the model's parametric knowledge. After retrieval, an agent can grade each document's relevance and filter out content that does not address the user's query. After generation, an agent can verify the claims in the response are actually supported by the retrieved context. This transforms RAG from a passive execution system into an active decision making system. The agent doesn't just execute a fixed sequence, it reasons about what to do, evaluates the outcomes, and adjusts its approach based on what it observes. Now let's examine the four foundational agentic design patterns that enable these capabilities. Now let's talk about the four foundational design patterns that enable agentic behavior in RAG systems. These patterns can be used independently or combined to create a sophisticated retrieval and generation workflows. So the first pattern is reflection. Reflection enables agents to evaluate their own outputs, identify error or gaps in reasoning, and trigger corrective actions. A reflection step might examine whether the retrieved documents adequately cover the query. It might assess whether the generated response addresses all aspects of the question. It might also check whether any claims in the response lack supporting evidence from the source material. In my experience, adding a simple reflection step can catch up to 20 to 40% of quality issues before they reach the user. The results will depend heavily on the quality of your reflection prompts and the capabilities of your underlying foundational model. So, the second pattern is planning. Planning allows agents to decompose complex queries into sequence of simpler operations. Consider questions that span multiple topics or require synthesizing information from different domains. A planning agent can break this into sub-questions, each retrieving from appropriate sources, results then synthesized into a comprehensive answer. The pattern is particularly valuable when you're dealing with multi-hop reasoning questions, where answering the final question requires first answering the intermediate questions. The third pattern here is tool use. Tool use gives agents the ability to select among different retrieval mechanisms based on query characteristics. Factual questions might route to a knowledge base, questions about current events might route to a web search, numerical queries might route to structural databases. Questions that fall within the model's reliable parametric knowledge can then bypass retrieval entirely for faster response times. The key insight here is that not every question needs the same retrieval approach, and giving the agent flexibility to choose and can significantly improve both quality and efficiency. So the fourth pattern here is multi-agent collaboration. Multi-agent collaboration distributes different aspects of the retrieval and generation process across specialized agents. One agent might handle query analysis, another agent might handle document retrieval, a third agent might handle relevance grading, and a fourth agent might handle response generation. An orchestrator coordinates the workflow between these specialized components. This pattern allows you to optimize each stage independently and can provide better observability into where things can go wrong. These four patterns combine to create systems that can handle queries far beyond the capabilities of linear retrieval approaches. In practice, most production agentic RAG systems use some combination of these patterns rather than just using one in isolation. Now let's look at the first architectural approach for implementing agentic RAG, which is query routing. Now let's talk about query routing architecture, which introduces intelligent dispatch at the entry point of the RAG system. The core idea behind query routing is that different types of queries should be handled by different retrieval strategies. When a query arises, a routing agent can analyze its characteristics and selects the most appropriate path forward. Let me walk through the typical routing destinations you might configure. Factual questions about specific topics in your domain should route to vector databases containing indexed domain knowledge. Questions requiring current information should route to web search APIs that can access real time content. Queries involving numerical analysis or structured data should route to SQL databases or analytical tools. And questions that fall within the language model reliable parametric knowledge can bypass the retrieval entirely for faster response times. The routing decisions should consider several factors. So the first factor is query type. For example, it should check if it's a factual question or an analytical question or an exploratory question or a conversational turn. Different types benefit from different retrieval strategies. So the second factor is actually recency requirements. Is the user asking about historical facts that won't change, or are the current events that require up-to-date information? And the third factor is source coverage, which of your available knowledge sources are likely to contain relevant information for the specific query. And fourth factor is confidence level. How confident is routing system that each path will produce good results? And the fifth factor is the operational constraints. For example, what are your latency and cost budgets for this particular query or user segment? Implementation typically uses a language model to classify incoming queries with structured output specifying the selected route. The classifier instruction describes available routes and the appropriate use cases, and the model returns a routing decision along with the reasoning. This reasoning can be valuable for debugging when routing decisions produce unexpected results. One critical implementation detail is fallback chains. Your primary route might fail to produce adequate results, either because the source is unavailable or because it doesn't contain the relevant content. You should design fallback paths that ensure graceful degradation. For example, if the primary vector search returns low confidence results, the search might automatically escalate to web search before giving up. In my experience, a well tuned routing system can reduce retrieval latency by 30 to 40% for queries that don't actually need full vector search, while also simultaneously improving the accuracy by directing specialized queries to appropriate sources. However, the routing classifier itself adds latency typically around 100 to 300 milliseconds depending on your model choice. So you need to ensure that the routing benefits outweigh this overhead. Now let's examine the corrective RAG pattern, which introduces the validation and correction after the document retrieval. Now let's talk about the corrective RAG pattern, which introduces validation and correction loop after the document retrieval but before response generation. Here's the fundamental insight behind this pattern. Traditional RAG retrieves documents and immediately uses them for generation, regardless of whether those documents actually help answer the question. Corrective RAG adds a grading step that evaluates each document's relevance before proceeding. The workflow should operate as follows. First, the system retrieves the documents using the standard vector search or whatever retrieval mechanism is appropriate. Second, a grading agent examines each retrieved document and produces a relevance judgment. This can be binary, either relevant or non-relevant, or it can be a continuous score indicating the degree of relevance. Third, documents falling below the relevance threshold gets filtered out before context assembly. Fourth, if too few relevant documents remain after filtering, the system triggers correction mechanisms rather than generating from adequate context. Let me walk through the correction strategies you should consider implementing. So the first strategy is query reformulation. The original query gets rewritten for different terms or expanded scope to improve retrieval on the next attempt. This might involve adding synonyms, removing overly specific constraints, or restructuring the question entirely. So the second strategy is source expansion. If the primary vector database does not contain adequate results, the system searches additional knowledge sources, perhaps web search, a different index, or specialized databases. So the third strategy is retrieval parameter adjustment. The system might modify similarity thresholds, increase the number of retrieved documents, or change the retrieval algorithm entirely. And the fourth strategy is the web search fallback. When internal sources are insufficient, external sources can supplement the knowledge base with broader coverage. The correction loop might iterate multiple times, with each cycle attempting different strategies until sufficient relevant context is assembled or a maximum iteration count is reached. You should set this maximum carefully. In my experience, if three correction cycles have not produced adequate context, additional iterations rarely help and simply add latency. The pattern significantly reduces one of the more primary failure modes in traditional RAG systems, which is responses generated from irrelevant context. When the system does not have good information, it now has the ability to recognize that fact and take corrective action rather than confidently generating an answer from tangentially related material. The trade off, of course, is latency. Each grading step and correction cycle adds processing time. You should expect corrective RAG to add anywhere from 500 milliseconds to several seconds compared to single pass retrieval, depending on how many correction cycles are needed. This is typically acceptable for high stakes applications where accuracy matters more than speed. Now let's look at self-reflective RAG pattern, which extends validation into the generation phase. Now let's talk about self-reflective RAG pattern, which extends validation beyond retrieval into the generation phase itself. Corrective RAG validates retrieved documents before generation. Self-reflective RAG goes further by validating the generated response before returning it to the user. This catches a different class of errors, specifically hallucinations and quality issues that emerge during generation process rather than during retrieval. After producing a response, a reflection agent examines the output against multiple quality dimensions. Let me walk through the key validation checks you should implement. So the first check is groundedness verification. This determines whether the claims in the response are actually supported by the retrieved documents or not. Language models are very good at generating plausible sounding content, but that content sometimes extends beyond or even contradicts the source material. Groundedness checking compares actually each factual claim against the provided context to identify unsupported statements. In my experience, this single check catches the majority of hallucination issues in production systems. The second check is query coverage assessment. This determines whether the response addresses all the aspects of the original question. Users often ask compound questions with multiple paths, and the initial generation might address some paths while missing others. Coverage checking ensures completeness. The third check is coherence evaluation. This assesses the logical consistency and clarity of the responses. Sometimes generation produces answers that are individually correct but don't fit together coherently, particularly for complex queries that require synthesis. When the reflection step identifies issues, the system has several response options. It might regenerate with modified instructions that emphasize the specific quality dimension that failed. It might retrieve additional context to fill identified gaps, or in cases where acceptable quality cannot be achieved, it might return a response acknowledging limitations rather than providing unreliable information. This last option is often preferable to returning a low quality answer, though might need to balance this against the user expectations as well. Iteration control is critical for self reflective RAG. You should prevent infinite loops by setting maximum retry counts and tracking whether quality improves actually iterations. If the quality plateaus or actually degrades, the system should terminate with the best available response rather than continuing to iterate. 2 to 3 reflection cycles typically capture most achievable quality improvements. Beyond that, you're usually hitting fundamental limitations of available information rather than fixable generation issues. This pattern is particularly valuable for high stakes applications where response accuracy directly impacts outcomes such as medical information systems, legal research tools, or financial advisory applications. The additional latency, which can be 1 to 3 seconds per reflection cycle, is justified when incorrect answers can carry significant consequences. Now let's examine adaptive strategy selection, which matches retrieval complexity to query complexity. Let's talk about adaptive strategy selection, which is about matching retrieval complexity to query complexity so you avoid both under-engineering and over-engineering for your responses. Here's the core insight. Not every query needs the same level of sophistication. A simple factual question with a clear answer in your knowledge base does not need multi-step planning, iterative correction, and self-reflection. But a complex research question requiring synthesis across multiple domains absolutely does. Adaptive RAG recognizes this and adjusts its approach based on what the query actually desires. Query analysis should classify incoming questions into complexity tiers that map to different processing strategies. Let me walk through a typical tier structure. So the first tier is simple factual queries. These are questions with clear, direct answers that likely exist in your knowledge base. For these, you should use single pass retrieval with standard generation. Skip the correction loops and reflection cycles for this. Just retrieve, generate, and return. Response times for this tier should typically be under 2 seconds. So the second tier is synthesis queries. These are questions requiring information from multiple topics or sources within your domain. For these questions, you should use parallel retrieval from different source areas followed by consolidation. You might include a basic relevance check, but you probably don't need full iterative correction. Response times for this tier typically range from 2 to 5 seconds. And the third tier is multi-hop reasoning queries. These are questions requiring chains of inference where answering the final question first requires answering intermediate questions. For these, you should use iterative retrieval where each step builds on previous results. Include the document grading and possibly correction loops here as well. Response times for these with this tier typically ranges from 5 to 10 seconds. And the fourth tier is exploratory research questions. These are open ended questions requiring broad investigation and synthesis of findings. For these, you should use exploratory retrieval with broad initial researches, progressively narrowed based on intermediate findings. Including a full reflection and validation here is desirable. Response times for this tier might even exceed 15 seconds, and users should be informed that comprehensive research does take time. The adaptive approach prevents two failure modes. The first failure mode is over engineering simple queries, where you add unnecessary agent calls that increase latency and cost without improving quality. The second failure mode is under engineering complex queries where single pass retrieval cannot assemble an adequate context for questions that generally need sophisticated handling. Strategy selection can be implemented through rule based approaches using query characteristics like length, question words, and entity counts. It can be model based using a language model classifier, or it can be hybrid combining simple heuristics with learned classification for ambiguous cases. In my experience, starting with rule based approaches and adding model based selection as patterns emerges from usage data works well for most teams. Now let's discuss the production architecture component that you will implement for implementing the agentic RAG at scale. Now let's talk about production architecture components required to run agentic RAG systems reliably at scale. The patterns and strategies we have discussed are conceptually elegant, but making them work in production requires significant supporting infrastructure. Let me walk through the critical components you should plan to implement. So the first component is Query Analyzer. This module classifies incoming queries, extracts key entities and concepts, identifies query intent, and routes to appropriate processing strategies. It's the entry point where all the adaptive strategy selection happens. You should design this to be fast, typically under 200 milliseconds, since it runs on every single query. The second component is Retrieval Orchestrator. This manages connections to multiple knowledge sources, handles parallel retrieval when queries span sources, and assembles retrieved content into coherent context for generation. In production, you might have vector databases, keyword search indices, structural databases, and web search APIs all available as retrieval targets. The orchestrator coordinates access to all of these. The third component is Document Grader. This evaluates the relevance of retrieved content, filters low quality results, and triggers re-retrieval when necessary. The grader needs to recalibrate carefully. Too aggressive and you will filter out useful documents. Too permissive and you will let irrelevant context pass through. You should expect to tune this based on your production feedback. The fourth component is Response Validator. This checks generated outputs against source documents, identifies unsupported claims, and manages the regeneration loop when issues are detected. The validator implements the self-reflection pattern we discussed earlier. The fifth component is state management. Agentic RAG involves multi-step processing, and you need infrastructure to track queries through this processing, maintain context across retrieval iterations, and store intermediate results for debugging and analysis. And you should also enable recovery from partial failures. If a correction loop fails midway through, can you resume from where you left off? State management makes this possible. The sixth component is error handling. Production systems need graceful degradation when components fail. They need timeout management for long running operations, and since you can't let a query run indefinitely, they do need circuit breakers as well to prevent cascade failures when external services have outages, and they do need structured error responses that inform the users when queries cannot be answered rather than silently failing or they just keep hanging and getting timeout. The seventh component is observability infrastructure. You should log all agent decisions for debugging, not just final outputs. When something goes wrong, you need to trace back though the decision chain to understand why. You should track quality metrics across the full pipeline and not just end-to-end accuracy. And you should enable A/B testing or different strategies so you can continuously improve based on production data. This infrastructure might seem like a lot, but it is. The agentic RAG system is significantly more complex than traditional RAG implementations. However, the complexity is manageable if you build incrementally, adding components as you encounter the specific problems they solve rather than trying to build everything upfront. Now let's conclude by discussing when agentic RAG actually provides value and when simpler approaches are better choice. Let's conclude by talking about when agentic RAG provides genuine value and when the added complexity might not be worth it for your use case. Agentic RAG introduces meaningful trade-offs that you need to consider carefully before adopting this approach. So the first trade-off is latency. Each agent call adds latency from additional language model inference. A simple query could be answered in 1 to 2 seconds with Traditional RAG might take up to 5 to 10 seconds with full agent processing. For some applications and user expectations, that additional time is acceptable. For others, however, it will be a deal breaker. The second trade off is cost. Each agent call consumes tokens that translate directly to API cost. A traditional RAG query might use one language model call. An agentic query might use 3 to 7 calls for routing, trading, generation, and reflection. This can multiply per query expenses by 3 to 5 times or even more. You need to understand your cost constraints and whether the quality improvements justify this increase. The third trade off is complexity. Agentic system requires more sophisticated monitoring, debugging, and maintenance. When something goes wrong, you're debugging a multi-step decision chain rather than a simple retrieval and generation sequence. Your team needs to be prepared for this operational complexity. Given these trade-offs, agentic RAG approaches are justified in these specific circumstances. So the first circumstance is when your query complexity genuinely requires multi-step reasoning or synthesis across different sources. If your users are asking simple questions, agentic approaches add overhead without improving quality. So the second circumstance is when accuracy requirements are high enough that validation loops catch errors worth the additional processing time. If appropriate answer is acceptable, the validation overhead might not be justified. The third circumstance is when your knowledge domain is dynamic enough that routing between sources and fallback strategies provide meaningful coverage improvements. If you have a single, well maintained knowledge base, routing complexity may not help. The fourth circumstance is when your users have sufficient latency tolerance for additional processing time. Real time chat applications have different constraints than research tools where users expect to wait. Agentic approaches provide less value in other scenarios. If queries are predominantly simple factual lookups that single pass retrieval handles pretty sufficiently, then the additional agent calls might not be needed and they might not be improving quality that much. If latency constraints require sub-second responses, you can't afford this overhead as well. If cost sensitivity limits per query budgets, the multiplied API cost may be prohibitive. And if your knowledge base is well curated and queries are predictable, the correction and fallback mechanisms may rarely reactivate. So my recommendation is to start with the simplest architecture that meets your requirements. Add agentic components incrementally as specific failure modes emerge from your production use case, and always measure the quality improvement against the cost and latency increases to ensure the trade-offs are actually favorable for your specific situation. There is no universal answer about whether agentic RAG is right for your application or not. It depends on your users, your domain, your quality requirements, and your operational constraints. But I hope this session has given you the framework to make that decision thoughtfully. So that was a session on Agentic RAG. If you have any questions or concerns, please let me know. Thank you and have a good day. Thanks.